Welcome to the lecture series on fluid dynamics. My name is Sandeep, and this course, Fluid Dynamics Part 1, is designed for a complete beginner in fluid dynamics. Okay, so the focus here is on the fundamental aspects, concepts, and also from an application point of view. Okay, so this video, the first video, is all about introduction to this course. Okay, so now to start with, these are the books I recommend to learn fluid dynamics if you are really new to fluid dynamics. The first one is fluid mechanics by Frankham White. This is an excellent book. Then you have Fluid Mechanics by Singal. This is also a very good book. And then you have Fluid Mechanics by Fox and McDonald's. These are really good books to start this subject. Okay, and if you want to learn some of the advanced topics, not all the advanced topics, that we will cover in the next course or the next series, where we will look into compressible flow and some more advanced topics. But some of the advanced topics which are discussed in this lecture series, you can have a look at the book by Fundamentals of Aerodynamics by John D. Anderson, and Boundary Layer Theory by Schlichting, and also Fluid Mechanics by Kundu and Cohen. Okay, so these are the books I would recommend to learn fluid dynamics, and especially for this particular lecture series. Now, what is fluid? Let us start with this fundamental question. What is fluid? Right? So we have learned what is fluid. We already know fluid. We are using fluid, right? So from our high school physics, we have learned that solid, you can see this is the structure of a solid here, right? So the atoms and molecules are very tightly packed in solids. And we also know that in liquids, the molecules are not that tightly packed as in the solids. It's loosely packed, you can move around. And then for the gases, it is really loosely packed, and it can really move around, or it undergoes a random motion. So this is what we know from our high school physics, right? And then fluid can take any shape. So what is fluid here? Fluid is liquid and the gas. So put together, either one, you can call it as fluid. And then we separate it from the solid. So the fluid can take any shape. It can take the shape of the container, right? So, and whatever, so it just flows. This is what we know from our school physics. As engineers, we should slightly step up. We should know a little bit better definition of fluid. So to know that, let us take a solid element or a small block of solid, and also a little bit of small block of fluid. Now we are going to apply tangential force here. So tangential force or the shear force. What is shear force, right? So we have two types of forces, you know about this, and we have the normal force. For example, this is a solid block, and if you are applying a force in the normal direction, right? So this is force normal. So you're putting or you're applying it in the normal direction or a perpendicular direction. You can do the same for the fluid as well, but you need to just put them in a container. You can put it in a container. So this is the fluid, and you can use some piston arrangement, and then you can apply the same normal force. But in this condition, when you're applying normal force, the fluid and the solid are going to behave very similarly. Okay, it will undergo some kind of deformation, but this deformation is based on the compressibility, but they are very similar in fluid and in solid. But when you apply tangential force is in the tangential direction, like not the normal direction. So when you apply tangential force, it's also called as a shear force. This is going to be different in solid and in fluid. So what will happen? Let us see. So in the fluid, you can see a tiny dot there. Let us represent as a particle in fluid, and let us see what will happen to this. You can see that under the application of this tangential force, the solid got deformed, and this deformation is proportional to the stress, or it's proportional to the force you are applying. But whereas in fluid, it has undergone continuous deformation. Even if you apply a very tiny tangential force, it is going to undergo deformation and a continuous deformation. So that is the big difference between solid and fluid. And now if you remove the force, what will happen? Solid will retain its shape. it will come back. But whereas the particle which moved, right, it is still there. So that means whatever you have applied, the shear force you have applied, and that deformation, it is not coming back. It is lost. That energy you have spent is already lost. And this is lost as dissipation, or it is lost in the form of viscous dissipation. So this is the big difference between solid and fluid. So to summarize it, you can say that solid is going to retain its shape when you take or remove the tangential force, but whereas in the case of fluid, it never regains its shape. The energy is lost as a viscous dissipation, as heat. And also the deformation in solid is proportional to the force, right? It is directly proportional. Whereas in the fluid, it is undergoing continuous deformation. And one more thing you need to note, stress is proportional to the strain in solids, right? So you apply a force, it will undergo deformation. The strain, it is directly proportional to how much amount of force you are applying. But in fluid, it is not the deformation, but it is the rate of deformation. So it is the rate of strain. So how fast it is, one layer is moving over the other layer. So if you can write it down, in case of fluid, you can write as the tau, the shear stress, is directly proportional to du by dy. It is the speed of the velocity gradient of different layers. Or you can write it as tau is equal to mu times du by dy, and this is known as Newton's law of viscosity. You don't need to know about it now. Forget about this equation. We are going to derive it from scratch, and we are going to understand it in a very detailed way in the coming videos. Now we have some clarity on the definition of solid and fluid. And without going much technical details in this video, let us look into the applications of fluid mechanics, right? Some of the interesting things. One interesting area is the aerodynamics. Everybody is passionate about aerodynamics. It's a very interesting area. And we start with very simple 2D airfoil, understanding the flow structure, understanding the forces like lift and drag force around an airfoil. And with this knowledge of whatever, the fundamental aerodynamics, you apply it on a real world application like civil aircraft. And you see how the flow structure is around, and you use it for the real world application for traveling, right? And similarly for the drones, understanding the aerodynamics, the forces, the thrust force of the drone, and then you use it for the real world application, for military application, for civil applications. And if you look into other aspects, other applications like the fighter jets or missiles, or even the in the space application, we are going to use the idea or the fundamentals or the application of fluid dynamics. And then not only in the space or aerospace application, right? We are also going to use the knowledge of aerodynamics or fluid dynamics in the aerodynamics of car, the shape of a car, developing the proper shape, aerodynamic shape of a car to reduce the drag, also to reduce the noise, the aeroacoustic studies. And similarly, if you look into hydraulics or hydraulic machines, you will see the application of fluid dynamics in pumps, in the turbines, in the hydraulic turbines like Kaplan turbine or Pelton turbine. All these areas you're going to use the knowledge of fluid dynamics. And even the machines like this, right, the bulldozers or the cranes, they're all working based on the hydraulics or fluid dynamics. And when you look into other machines like thermal machines, thermal turbo machines, again you will see like there are multiple compressors. There are at different stages, right? Compressors are there. Then you have combustion chamber. You have turbines, and they are all operating based on the fundamentals of fluid dynamics. And also heat transfer. This is another interesting application. Forced convection, the removal of heat by using air or liquid or phase change material, So they all are coming under fluid dynamics, or they're basically the application of fluid dynamics. Another interesting application is in the area of civil engineering. You might be familiar with this video. This is the famous collapse of the Tacoma Narrow Bridge in 1940 because of fluid structure interaction. So it's a combination of fluid flow and the structure interaction. It's called as aeroelastic flutter, and it resulted in the collapse of a bridge. Nobody believed at that time. There are other applications also in the civil engineering, like construction of a dam, or HVAC, room air circulation or ventilation system, and for the building aerodynamics, and there are many more applications in the civil engineering. Now let us have a broader picture of all the industries where you are going to use fluid dynamics. If you look into renewable energy, it is there. If you are looking into shipbuilding, you have it there. If you look into the industry, aerospace industry, it is there. For medical industry, it is there. For automotive industry, you have fluid dynamics. For nuclear industry, you need to use fluid dynamics. Whether it is chemical engineering, it is fluid dynamics, it is there. So it has got vast application in all the kind of industries, wherever you're going to use fluid flow, right? Whether you're going to use liquid, or whether you're going to use air or any other fluid, you're going to use the concept of fluid dynamics. And forget about the industry right now. What about our daily life? We start our morning with the knowledge of vortex flow to flush the toilet. And we also take shower with the knowledge of liquid atomization, right? The breakup of droplets. So, and then after that, you prepare a coffee with the knowledge about, again, fluid dynamics with the turbulent mixing, and also about interaction of tiny particles, the porous particle, and thermodynamics and fluid dynamics in the coffee. And if you look into cooking in the kitchen, again, phase change process. You are working on boiling, which is again an interesting fluid dynamics phenomena. Or if you look into, if you are smoking a cigarette, you need to know a lot more. You are good at fluid dynamics, you know about fluid dynamics, you know about combustion, you know about chemical kinetics, you know about heat transfer, you know about natural convection, and many things. A lot more physics involved there, and the coupling of fluid dynamics with many more physics. And what about drying the hair? Again, heat transfer and fluid dynamics. It is forced convection. So again, knowledge. So, even if you don't know the technical details of all of these, we are basically applying it in our life. So fluid dynamics is everywhere. Now look at the nature. It looks like birds also know fluid dynamics. They fly in a V formation, and this V formation helps them to travel much longer distance, especially for the migratory birds. The bird which is flying in the front is going to take all the loads, or a lot more load compared to the other birds which is flying behind them. And then they will keep rotating the position. And this helps them to travel to much longer distance. And this is all again based on the fundamentals of fluid dynamics. Another example is the lotus plant. If you see the leaves of the lotus plant, they are very, very clean. Why? Because these leaves behave as a hydrophobic surface. And when you drop water on it, it just rolls off. It's not going to stay there. So this makes it, for applications like this, we can use it for special coating, hydrophobic coating, which is water resistant. Another example in the nature is these tall trees. Go to a forest, you see very, very tall trees, right? Ever imagine how they are getting the water all the way on the top to the leaves there? Again, fluid dynamics. It involves a lot more complicated physics here. You have flows through xylem and phloem with capillary effect. There is, physics involved, again, osmosis connected to fluid dynamics. There is evaporation from the surface of the leaves, and this is called as transpiration. And all these helps in the circulation of water. Again, fluid dynamics in a much detailed, much complicated way. Look at this example of the dandelions. The seeds get transported to a much longer distance because of the help of fluid dynamics. It's a very interesting field. A lot of research is going on, especially at the University of Edinburgh, where they are doing a lot of experimental and computational study on this. Now look at our own body. The human body is also consists of so many arteries and veins, right? It's all connected. And what is flowing through it? The blood flow. It's also very complicated. The blood is nothing but non-Newtonian fluid. It's a fluid. So the flow of fluid, the blood through the body, is also studied by fluid dynamics in collaboration or in connection with the medical specialist. And not only the blood flow, you also study about the air flow through the lungs. This is again very interesting area. And there are many other applications of fluid dynamics in the medical field, for preparing something artificial, like artificial kidney, artificial, any devices, medical devices. You need to know the knowledge of fluid dynamics. Even, the sweating and evaporation, right? What is happening after sweating? You're regulating the temperature of your body. This is again principle of fluid dynamics. So a lot more to do, even in our human body. And now if you want to keep this body healthy, what you normally do? Sports, right? So if you are into cricket, you have this, already this example, right? The in-swinger and the out-swinger. Again, it is based on fluid dynamics. What we will do, we'll keep one side shining, right? You rub it and then make one side shining and the other side is left as rough. So what will happen? See this example, right? The legendary bowler, Wasim Akram, and he is able to swing the ball. It's not going direct, it's taking a path, a different path. It's swinging to one side. You can do it in swinger, swinging, coming towards you, or you can make it out swinger, going away from you. And you can see Sachin Tendulkar got, also bowled because of this. So how does it work? Again, based on the fluid dynamics. So you can see the rough side of the ball, there is flow separation and there is a lot of turbulent flow, and that helps, in balance of the force. So there is a kind of pressure difference between one side of the ball and the other side of the ball, which pushes, there is a net force because of that, and it pushes the ball to swing to one direction, especially to the rough side direction. Now look at this one, an example from football, the magic goal by Roberto Carlos. See the ball, the trajectory. It's turning all the way around and a magic goal. How is it possible? It's also known as, one of the impossible goals at that time. Now you can see many more examples of this ball taking the curved path. And what is this? How did it happen? This is based on Magnus effect. This is when a ball is rotating, again, there is a net force into one direction, which will help to take this trajectory, take this curved path. Another interesting example in the sports is golf ball. You see that golf ball travels, double the distance compared to a smooth ball. This is, you can see the dimples on this golf ball. This creates turbulence, and that helps in, much longer distance. It travels twice that of, approximately twice as that of a smooth ball, based on the principle of turbulence and aerodynamics, again, fluid dynamics. Now we have seen a lot of examples, some from the industry, some from the nature, some from our own body, some from sports, and many other applications, right? So these are all where you see fluid dynamics. Now, how do you study it? How do you analyze it? How do you learn this, and how do you design certain things? This is where there are three methods in fluid dynamics, and they are CFD, AFD, and EFD. So what are they? CFD means computational fluid dynamics. This is where you're going to use computers and computer simulations to study fluid dynamics. We'll come to that. And you have analytical fluid dynamics. This is the AFD. This is where you're going to solve the equations. You're trying to solve the equations, the governing equations, and do a lot of approximations to get quick solution. And many cases you cannot do the analytical solution. You have to do a lot of approximation to get some analytical result. Okay? And then you have the experimental fluid dynamics. This is where you're going to do real world experiments. You're going to analyze something. You're going to do experiments and then learn something, right? So these are the three different methods to study fluid dynamics. So if you look at the analytical fluid dynamics, this is where you're going to take the governing equation, the partial differential equation or the differential equation. You're going to integrate it and then solve it and find some kind of solution. But here, definitely you need the mathematical knowledge. It's not just the math knowledge. You should be also a perfect engineer. You should know what approximation you need to do, right? And you need to know what are all the conditions, so that you can get some solution which will give you an idea about the physics, and then attack that part and then solve the problem, real world problem. So this is a very effective tool. Even in the industry, people are working on analytical solution and 1D solution, right, from analytical solution. So here it's all about mathematics and a little bit of programming. And the next method is the experimental fluid dynamics. This is known as the truth, okay, the ultimate truth, because you're going to work on a real condition or maybe a scaled down models where you're making the model into a smaller dimension, because using the dimensional analysis, and then you work on this and then try to understand the physics. You should also know a lot about the equipments, about instrumentation. You need to know about optics and things like that. Those knowledge will help you to really understand the physics and visualize things and study about the fluid flow and heat transfer and things like that. And this is what everybody will rely upon, the experimental fluid dynamics. But the problem here is it's quite expensive. You cannot test everything, right? So what is the solution? You have the computational fluid dynamics. This is again one very nice set of animations from NASA. And these are very high fidelity simulation, which normally you cannot do easily with your computer. But what is computational fluid dynamics? Computational fluid dynamics is where you're using computers, you're solving the governing equations of fluid flow, and you analyze it, you visualize it, the physics. This is very, very powerful and much cheaper compared to experiment. And then you can do a lot more testing. And definitely you need to validate it. Go back to the experimental fluid dynamics. You need to test it, validate it, and but in the whole process of using computational fluid dynamics and experimental fluid dynamics, you can reduce the overall the design time or the product development time. So it's very, very effective tool in the industry, computational fluid dynamics. So people use computational fluid dynamics, they use the experimental fluid dynamics and also the analytical solution, and use the analytical solution also into 1D simulations, this kind of much more approximate simulations. Now let us look into the opportunities of fluid dynamics. There are plenty of opportunities in fluid dynamics. Many unsolved problems are there. A lot of research is happening in fluid dynamics. And also the latest trend, the machine learning and AI, the artificial intelligence. You're clubbing it with fluid dynamics. A lot of research is going on in this area. And this opens up another interesting area where you can use your skill in programming and in mathematics, and then use it for fluid dynamics. And plenty of other opportunities, right? So look into the job opportunities. You can work as an experimentalist, you can work as a researcher, you can work as a design engineer, you can work as a CFD engineer, you can work as a software engineer, and you get much diverse possibilities when you are into fluid dynamics. And definitely academic, you can be into teaching and other job as well. So a lot more opportunities, if you learn fluid dynamics. And the last one is about the computation. Just look into only the market of CFD, the computational fluid dynamics. Right now it is a $3 billion market, and in 2030 it is believed to be $5 billion market. And see the opportunity. This is just computational fluid dynamics. Now look at the product development, different companies involved, different research group involved, experimental fluid dynamics and other things, everything put together. It's a huge market. So you have a lot of opportunities if you work in this field or if you learn fluid dynamics. Okay, so I hope I have given enough motivation for you to learn this subject, to learn fluid dynamics. So that's all for this video. See you in the next video.